Hello everyone, welcome back to Tales of Chemistry. Now, let us continue with isotonic solutions. If there are two solutions at same temperature, then and if the osmotic pressure of the two solutions are the same, then it is called isotonic solution. Solutions having same osmotic pressure at a fixed temperature, at a particular temperature, are called isotonic solutions. Since osmotic pressure remain the same, we have written here pi 1 is equal to pi 2. But pi is equal to CRT, concentration of solution into universal gas constant into absolute temperature. Now, C1RT is equal to C2RT when you substitute pi by CRT. Since temperature remains constant and ideal gas universal gas constant is anyway a constant, C1 is equal to C2. So if two solutions are said to be isotonic, then the concentration of the two solutions are equal. Now, the next is hypertonic as well as hypotonic solutions. When you compare two solutions having different osmotic pressure, then the one with higher osmotic pressure will be called hypertonic solution. Two solutions, okay, at the same temperature, but they have different osmotic pressure. The one which has more osmotic pressure, greater osmotic pressure, will be hypertonic solution, and the one with less osmotic pressure is a hypotonic solution. So I hope these three terms are clear: isotonic solutions, hypertonic solutions, and hypotonic solutions. Now, some phenomena that happens, what we have seen, explanation to such phenomena on the basis of osmosis. First of all, we all have seen this raw mangoes in pickle. Raw mangoes shrink. Why will that, a process happen? This happens when mangoes are put in concentrated salt solution. Excess of salt is dissolved in water. Concentrated salt solution is prepared. Into that, when mangoes are dipped, the water content within the mango flows through the skin of mango, through the semi-permeable membrane of mangoes towards the salt solution or salt water. So raw mangoes shrink when placed in concentrated common salt solution due to outflow of water through a semi-permeable membrane of mangoes. Similarly, people consuming a lot of salt, they develop a swelling of their tissues. This is due to the retention of water in their tissue as well as in the intercellular space due to osmosis. So these are all not very frequent questions. These are kind of like, they can ask as give reason questions. So just to be familiar with the osmosis, process of osmosis, these examples were taken. Now, reverse osmosis is a very important property or phenomena that we need to know. What is happening in osmosis? Through a semi-permeable membrane, solvent particles are flowing from dilute solution to concentrated solution. And what is osmotic pressure? When you apply pressure on the walls of the semi-permeable membrane, from the concentrated solution side, you can stop the process of osmosis. So that pressure which is applied is called osmotic pressure. But when you apply pressure which is greater than osmotic pressure will just stop osmosis. But when you apply pressure which is greater than osmotic pressure, the solvent, okay, from the concentrated solution will start flowing to dilute solution. Or what I have written here is solvent from solution starts flowing towards pure solvent. Suppose you have taken pure solvent on one side and solution on the other side. Due to reverse osmosis, from solution, solvent can flow to the, pure solvent side. This is called reverse osmosis. Reverse osmosis is used in water filters. This is useful to get pure water from seawater, which is called desalination of seawater. So reverse osmosis is a very regular question in the board examination. Last part in solution lesson is abnormal molecular masses. Now, you would have noticed that the formula for any of the colligator property, let it be relative lowering or let it be elevation in boiling point, depression in freezing point, whatever is the property that can be used to find out molecular mass of the solute. But accurate values of molecular mass can be calculated only if the solution is dilute. Right? Every single explanation, started with this for dilute solution. So, colligative properties are applicable only for dilute solutions. Second, and the most important one is the solute must not associate or dissociate in solution. The solute must remain as it is in solution. So what does this mean? Solute must not associate or dissociate. There are certain solutes like our KCl or CaCl2, etc., ionic compounds. The moment you dissolve them in water, they produce ions. So, 1 mole of KCl, suppose your solute is KCl and you're taking 1 mole of KCl, and that KCl will dissociate to give you 2 moles of ions. So number of particles are increasing from 1 mole of solute. In effect, you are finding 2 moles of solute in solution. CaCl2 on the other hand will give you Ca2 plus and 2Cl minus, which means 1 mole of CaCl2 is producing 3 moles of particles, 3 moles of ions in solution. So that is example for dissociation. Similarly, if we take an acid or a compound like acetic acid, CH3COOH. Okay, so in the case of CH3COOH, what takes place is association. Two acid molecules connect together, join together, and they exist as one entity. So, 2 moles of acetic acid, if taken, in effect, you will have only 1 mole. 2 moles will give you just 1 mole when in solution. That is called association. Now, whether the solute undergoes dissociation or association, the molecular mass or the number of particles are going to change. When the number of particles change, this is called abnormal molecular mass. So let's read this. Discrepancies arise when the solute associate or dissociate in a solvent, as colligative properties depend only upon the number of particles. Number of particles are changing due to association or dissociation. Accordingly, the molecular mass will change. So they are expected to show certain deviation. As the number of particles change, colligative properties will also show certain deviations. These deviations will influence the molecular mass. So such discrepancy in molar mass or molecular mass is called abnormal molecular mass. So this is because of association or dissociation. Now, to explain or to compensate for this abnormality, a factor called Van Hoff factor is introduced. Van Hoff factor is introduced to express the extent of association or dissociation of solutes in solution. Now, the letter that we use, the alphabet that is used to represent Van Hoff factor is I. I, Van Hoff factor, is equal to observed. Observed means experimental. Experimental colligative property by theoretical colligative property. So the theoretical is a normal one, which you are expecting from the formula. Observed colligative property is the experimental one. So Van Hoff factor is a ratio between observed colligative property and theoretical colligative property. Now, we know this variation in colligative property is affecting the molar mass as well. So I can also be calculated by dividing theoretical molecular mass with observed molecular mass. That is, I is also a ratio between theoretical molecular mass and observed molecular mass. So both these relations are very important. You need to learn both those relations. Now, using Van Hoff factor, all the formulae or all the equations for colligative property can be modified. So the first one, with the relative lowering of vapor pressure, initially or previously what we have learned is relative lowering of vapor pressure is equal to mole fraction of solute. The modified one is relative lowering is equal to I Van Hoff factor into mole fraction of solute. Then elevation in boiling point. Previously, this is what we have studied. Molar elevation constant or ebullioscopic constant into molality. Now we are introducing Van Hoff factor also into that. So I Kb into M, that is elevation in boiling point. Depression in freezing point. The third colligative property that we studied, delta Tf is equal to I Kf into molality. Pi osmotic pressure, the last colligative property that we have learned, pi is equal to I CRT. I Van Hoff factor, C concentration of solution, R universal gas constant, T is the temperature in Kelvin scale, absolute temperature. So all these modified equations are to be studied, kept in mind, and I is Van Hoff factor, which is calculated either by this relation, observed colligative property by theoretical colligative property, or it is theoretical molecular mass by observed molecular mass. Now, the last part here is degree of dissociation, as well as we need to know degree of association also. Degree of dissociation is, the fraction of the total substance that undergoes dissociation. What we mean here is, suppose I'm taking, say, 100 moles of the solute which undergoes dissociation. 100 moles of KCl are taken. It is not compulsory that entire 100 moles of KCl will undergo dissociation. Probably 99.25% will undergo dissociation, and the remaining 0.75% will remain without any dissociation. So degree of dissociation is defined as the fraction of total substance that undergoes dissociation into ions. Okay, once again, it's not compulsory for 100% dissociation to happen. So from the given sample, what percentage of the solute is undergoing dissociation? That is calculated using the formula alpha is equal to I minus 1 by Z minus 1. I, Van Hoff factor, and Z is the number of ions formed after dissociation. Example, NaCl will produce 2 ions. So for NaCl, Z is equal to 2. For CaCl2, Z is equal to 3. Okay. Whereas if it is glucose or urea, such compounds, Z will be 1, because these compounds do not undergo any dissociation. They do not undergo any association also. So I hope this part is clear. Degree of dissociation. Then degree of association. Degree of association is the fraction of total number of molecules which combine with each other to form associated molecules. Same thing. Out of that 100 moles of whatever, say, acetic acid that you have taken, it's not compulsory for all that molecules or all 100 moles to join together and exist as associated molecules, right? Okay, so here, the formula to calculate alpha is equal to n into 1 minus I by n minus 1. N into 1 minus I by n minus 1. So n here is number of molecules associating. Say, for example, if we take acetic acid. Okay, for acetic acid, N is equal to 2, because 2 acetic acid molecules are joining together. So this process is called association or dimerization, to be very specific. 2 molecules are joining together and it exists as one unit. If 3 molecules combine together and exist as a one, it's called trimerization. All right. So this formula important. These are actually the easiest method of calculating the degree of dissociation as well as association. So with this, the entire lesson solutions is completed. Thank you, and please stay tuned for important questions from this lesson.